So I want to walk through the check your understanding together so that hopefully we can wrap our heads around what it is that you guys need to do on that homework for tomorrow. Fascinate.com claims that 84% of teenagers think highly of their mother. To investigate this claim, a school psychologist selects a random sample of 150 teenagers and finds that 132 think highly of their mother. Do these data provide convincing evidence that the true proportion of teens who think highly of their mother is greater than 0.84? State appropriate hypotheses for performing a significance test. Be sure to define the parameter of interest. So we have two hypotheses. We have the null hypothesis that we use HO to represent, H with a little O next to it. And then we have the alternative hypothesis. We use HA to represent that, H with a little A next to it. The HO is always going to be whatever is claimed in the problem. What is the claim being made here? Way at the beginning. 84% of teenagers think highly of their mother. So our null hypothesis is that P, the true proportion, is 0.84. Do the data provide convincing evidence that the true proportion of teens who think highly of their mother is greater than 0.84? They're telling me there what the HA is. The HO and the HA will always have the same numbers. The HO will always be an equal to, and the HA is going to be one of three things. It'll either be a greater than, less than, or not equal to whatever the HO was. So in this case, because it says greater than 0.84, the HA is that P is greater than 0.84. Sometimes it won't say that greater than or less than. And the way you're going to tell the direction is by looking at what your sample statistic is. So our P hat in this case. How would you calculate P hat here? 132 over 150. What is 132 divided by 150? .88. So I would know to put a greater than for the HA, even without that last sentence, because 0.88 is greater than 0.84. The sample statistic P hat is bigger than my HO. All right, then it says we also need to define the parameter of interest, which is P. Oh, sorry, I wrote P hat there, and I should not have written P hat for the HA. That should just be P. My apologies, guys. I am so sorry. I got excited with the hats, apparently. What is P here? The first three words, when I ask what P is, first three words should always pop into your head before we even go look at the context. The true proportion. First three words should pop in your head. Anytime we're defining P, it is the true proportion of what here? Of teenagers that think highly of their mother. True proportion of, and don't forget to stick all in there. Whenever we are talking about our parameter, it's always talking about the whole population, and you do need to make that very explicit by using that word all. Number two, do the data provide some evidence for HA? Explain. Well, here's our data. That's our P hat. That's what we collected. And when we divided that, we got a P hat of 0.88. Does that provide some evidence that P is actually greater than 0.84? Yes. Sample proportion is greater than the HO. All right, scooting on to number 3. Before I put number 3 up on the screen, I just kind of want to read through it, and I want you to look up at the top of your page to help us figure out what we're going to write for number 3. It says, The school psychologist performed the significance test and obtained a p-value of 0.091. Interpret the p-value. P-value, by the way, is telling us the probability of the event if we assume the HO is true. So what's the probability of seeing a p-hat this high if the true proportion is actually 0.84? That's what a p-value is. It's the probability of that sample statistic occurring if the HO is true. So they got a p-value of 0.91. Interpret this p-value. Look up at the top of the page, up in the box that says Quick Notes. Look on the right-hand side. It says interpret p-value. So we're going to walk through this sentence here. It starts with, assuming HO is true, p equals, what is p here? Look at number 3. What is our p-value? 0.091. Or sorry, p, I'm getting confused. 0.84 is the value for lowercase p, the proportion. Yes. Sorry, I got ahead of myself in this little sentence here. Assuming the HO is true, p equals 0.84. There is a, and now we put the p-value in, 0.091 probability of getting a p-hat of, what was our p-hat? 0.88 or more extreme, purely by chance. This in here should match your HA. So as you're interpreting P, as you're interpreting the p-value, assuming the HO is true, tell me what the HO is. There is a p-value probability, because remember, p-value is telling you the probability of an event, of getting a p-hat of, and then we're going to talk about our p-hat, 0.88, and then or greater, because our HA was greater than, and actually that line should only be underneath the or greater than here. Scoot that over. Purely by chance. All right. When we did confidence intervals, we had a confidence level. 95% was really common. We also did 90%. We did 99%. I think one of the problems we did had an 80% confidence level. When we are doing significance testing, we have an alpha level. And it kind of mirrors what we were doing with our confidence level. If I have a 95% confidence level, that would be an alpha level of 5%. Together they make 100%. If I have a confidence level of 99%, the alpha level would be 1%. So these kind of go together. We are often going to use an alpha level of 0.05 or 5%. Remember, when we're looking at these, if you're going to change them into percentages, you move the decimal 2 places. So this would be the same as 5%. Do the results provide convincing evidence that the true proportion of teens who think highly of their mother is greater than 0.84? So we're going to compare the p-value up here from number 3 with the alpha level, 5%. At what point do we get suspicious? When it's bigger or smaller than 5%? Smaller. If it's smaller than 5%, it has less of a probability of occurring just by chance. And if the probability of it happening by chance is really small, I think there's another explanation for this most likely. And that would be our alternative hypothesis. So if we have a p-value of 0.091, how does that compare to the alpha level 0.05? It's greater than. So because 0.091 is greater than 0.05, we fail to reject the HO. And we do not have convincing evidence that the true proportion of teens who think highly of their mother is greater than 0.84. what would our conclusion have been if the p-value had been 0.03? We would reject the Ho. So I would say I'm only going to say this once, but I won't. I'll say it a lot because it'll help us remember it. When the p is low, reject the Ho. When the p is low, you reject the Ho. You never, ever, ever will accept the Ho. Yes, I said that for emphasis. You never accept the Ho. You fail to reject, but you never accept. You either reject or fail to reject. I got observed one year teaching this lesson. That was fun. Thankfully, the person doing my observation thought it was funny. All right. So far, so good? All right. We're going to spend most of the rest of our time now talking about how you come up with this p-value. Yesterday, we looked at how to come up with a p-value through simulation. We made our dot plot, and we looked at how many dots were at that null hypothesis, the Ho or less, or sorry, the observed result, p hat or less. So we used simulation for that. Let's flip over to page 5. It says, in our introduction to significance tests, we used simulation to estimate a p-value to decide whether or not I was exaggerating about my claimed 80% free throw percentage. I made 32 out of 50. Today we're going to use a formula to find the p-value. So let's write out these hypotheses and be sure to define the parameter. What's the Ho here? What's the claim being made? Yeah, that p is equal to 0.80. What would the Ha be then? Would the Ha be that it's greater than, less than, or not equal to 80%? We could do not equal to. I'm going to go with less than on this one because based on the p hat that we have, that 32 out of 50, that's a lot lower than I would expect if the p-value was really 0.80. I don't have any kind of counter argument to say, or it's way over. Most of the time we're going to be looking at greater than and less than. So the Ho is that p is 0.80. The Ha is that p is less than 0.80. I don't know why I wrote a greater than there. Less than. I'm finding mistakes all over the place today. What is the parameter here? True proportion of, yep, all free throws that Ms. Bolt makes. True proportion of free throw makes for Ms. Bolt. Want to get that all in there though. Whenever we're doing a significance test, we will always assume that the Ho is true. There always has to be this assumption at the beginning that one of these pieces is true, and we're always going to assume that the Ho is true. And then we go looking for evidence to see if we have evidence that it's not true. Do we have a random sample here? Yes. We have a random sample. Why is a random sample important? Yes, so we can generalize to the population of all free throws. Is the 10% condition satisfied? Yeah, what would I need to do to check that? 10% of all free throws has to be greater than or equal to 50, the sample of free throws. So 50 is less than or equal to 10% of all free throws shot by Ms. Bolt. So this condition has been met. Why is that important? Sampling without replacement is okay, so we can use our formula for standard deviation. Sampling without replacement is okay. And then checking the large counts condition. How do we check large counts? N times P, what's that on this one? N times P would be which one are we assuming is true? 0.80. We're assuming the HO is true, so N times P is going to be 50 times 0.80. That comes out to be 40. That's greater than or equal to 10, so we're good there. N times 1 minus P would be what? Yep, 50 times 0.20 gives me 10, which is greater than or equal to 10, so we meet our large counts. When we were doing our confidence intervals, remember we had no idea what P was. We had no clue, so we had to use P hat to estimate it. Here, we're making a claim that we think we do know what P is. So we're going to use P from the HA. If you think you know P, use P, not P hat. If you don't know what P is, you don't have any clue what P is, then you have to use P hat as an estimator for it. And if you have no clue at all, you don't have P or P hat, no data at all, then we use 0.5. We use our conservative estimate. Why would it be important to pass the large counts condition? What are we checking for there? We're checking for normality. So the sampling distribution of P hat is approximately normal. What would the mean of the sampling distribution be? What's the mean of P hat? Asking you to go back before break. That was chapter 7 stuff that we tested on before the final exam. The mean of P hat will be whatever P is. What's our P here? 0.80. So mean of P hat is just P, which is 0.80. And remember, we're using P, not P hat. Says we also need to find the standard deviation. What's the standard deviation formula again? Square root P, not P hat this time, because we think we know P, so we're going to use P. P times 1 minus P over N, yes. The standard deviation, lowercase sigma, of P hat is the square root of P times 1 minus P over N. And again, we're using P because we think we know what P is. We think we know the true proportion. And so we're going to sub our numbers in here. Square root of 0.80 times 0.20 over 50. And when you think you have it, let me know. Yep. Yeah, 0.0566 or 0.057, depending on where you round it. I'm going to use 0.0566. Use the mean and the standard deviation you calculated to label the normal curve below. Right here, we're going to do the sampling distribution of P hat. Remember, we said the sampling distribution was approximately normal because we passed our large counts condition. So since it's normally distributed, I have my N here. Mean and standard deviation with labels, mu and sigma. What's going straight down the center here? the mean. And what is our mean? 0.80. So I have 0.80 right down the center. And then we want to get 1, 2, and 3 standard deviations labeled to the right, and 1, 2, 3 standard deviations labeled to the left. So what do I do if I want to go to the right? I'm going to add the standard deviation onto it. So 0.80 plus 0.0566 gives me 0.8566. And then I add the standard deviation again to go out to this next line. What do you get if you do 0.8566 plus another 0.0566? 0.9132. And then we add another 0.0566. 0.9698 approximately. And now we want to go backwards. So now instead of adding, what are you going to do 3 times over? Subtract. Go ahead and fill those in, and then I'll put my answer up on the screen here in about 30 seconds. All right, so going down the left side, you get 0.7434, and then 0.6868, and then 0.6302. Where would that p hat of 0.64 fall? Yeah, like over here somewhere, right? Pretty close to that 3rd standard deviation. And which way did our inequality go for ha? Less than. So I'm going to shade this tiny little bit of tail over here. That area that I just shaded in, that little tiny bit, that's the probability of getting a p hat of 0.64 if the true value for p is actually 0.80. Does that look like a very big probability? So before we even calculate a p-value, do you think we're going to reject or fail to reject? I think we're going to reject. All right, we labeled this on the normal curve. Now to actually find exactly how many standard deviations away we are, that's what a z-score does. Do you guys remember calculating z-scores? Z-score, we take our statistic, our p hat, you subtract the parameter, p. So I have p hat minus p over the standard deviation. Square root of p times 1 minus p over n. We already know p hat, that's 0.64. What's p again? 0.80. And we already calculated our standard deviation up here. So I can just pop those numbers in. 0.64 minus 0.80 divided by 0.0566. This tells me how many standard deviations away we are from p. Yes? Why is it not on both sides? Because we had, on our alternative hypothesis, we had strictly less than. If it was a not equal to, then we would be doing the tails on both sides. We decided to make it less than because our p hat was less than. If they say in the question stem somewhere, is there evidence that it is different from or not equal to, that's when we'll use that not equal. Most of the time we're going to be using a greater than or a less than, so we'll only be looking at one of those tails. That is a fantastic question. What did you guys get for z-score? Yep. 2.827, 2.83. Negative, meaning we are which side of this normal curve? On the left. So what this is saying right here is from the center of this normal curve, we counted over almost 3 standard deviations. 1, to almost all the way to the third one. And then we shaded everything that was less than that because, again, our alternative hypothesis was a less than. How would I find the probability of that shaded space? Does anybody remember? Normal CDF. Normal CDF. What would our lower bound be? Negative a lot, so negative a million. What's our upper bound? 0.64. And then mean? 0.80. And standard deviation? 0.0566. Write down what you're doing on the calculator so that the reader understands exactly what you're doing and what all those different numbers mean. And then we calculate this. And what do we get for p-value? Yeah, 0.002. That is the p-value. That is the probability of me making 32 out of 50 shots if my true free throw average is 80%. And so when we talk about our conclusion, the first thing we're going to do is we're going to bring evidence. This is where I kind of think about significance tests almost like a court case. There's an assumption made in a court case. You always assume the defendant is innocent, right? There's always an assumption at the beginning of the court case. And then the prosecutor and the defense attorney, their job is to bring evidence, right? Prosecutors trying to bring evidence to show that the defendant is actually guilty. We need to bring evidence in our conclusion here. So we're basing our evidence on this p-value here, 0.002. How does that compare to an alpha level of 0.05? It's less than. It's substantially less than, right? It is less than. Because it's less than 5%, did this probably happen by chance? No. So are we going to reject the null hypothesis? Are we going to reject the HO, or are we going to fail to reject? We're going to reject it. We think that P is not actually 0.80. Because 0.002 is less than 0.05, we reject HO, and we do have convincing evidence that I am less than an 80% free throw shooter. We are going to do number 10, and then we're going to call it a day. We will do the check your understanding tomorrow. I do want to do number 10 and then just flip it over real quick so that we've seen the quick notes. And then we'll do the check your understanding to practice more tomorrow. But we should have gotten through everything that you guys need now to be able to do the homework. You do not have to calculate a p-value, I don't believe, on this homework. That comes on the next homework. You guys okay if we go look at number 10? Number 10 says, suppose that I really made 36 out of 50, or 72% of the free throws. Calculate and interpret the p-value and make a conclusion. So what would change here if it was really a 72%? Or sorry, if I really shot 72% instead of 64%? Would anything up here change? No, because this is using P, not P hat. So if P hat changes, this still doesn't change. Would anything change down here? Which things would change? Yeah, my Z value, what it comes out to be, is going to be different. because which pieces over here are different? Just the p hat. Only this number right here, that 0.64, is going to be replaced with 0.72. I want you guys to find the z-score, and then I want you to use that, do normal CDF to find a p-value on number 10. Find your new z-score. Use that with a normal CDF to calculate your new p-value, your new probability value. Does anybody have a new z-score? About negative 1.4 approximately. So if I go back and I look at this normal curve, I see that 0.72 is going to fall about here-ish if I look along that bottom axis, which is 1 and almost half standard deviations away. So z-score got about negative 1.4, negative 1.41, and that gives you a p-value. Would you expect it to be bigger or smaller? Bigger p-value because more of the area under the curve would be shaded. What is the p-value this time? Yep, 0.079. I think I got, no, that's exactly what I got. When I did it one other time, rounding slightly differently, I got 0.081. It's just where I rounded. I think it was on my standard deviation. I rounded to 0.057 instead of 0.0566. The difference in p-value between a 0.079 and a 0.081, that's not a big enough difference for anybody to care. Those are so close together. All right, so now we're going to interpret the p-value and we're going to make a conclusion. You might want to look back at page 4 where it has the stems for how to interpret a p-value and make a conclusion. How does interpreting my p-value start? Assuming the HO is true. What's the HO again? P equals 0.80. Include that in there. So assuming the HO is true, parentheses, P equals 0.80. There is a .079 probability of getting a p-hat value of 0.72 or less purely by chance. That sentence right there interprets the p-value. Assuming the HO is true, our whole normal curve is based on the HO being true, with 0.80 right down the center. If we start with that assumption, then getting a p-hat value of 0.72 or less just by chance has this probability, which is about what percent? 7.9, so about 8%, right? Right around 8%-ish. So are we going to reject or fail to reject? Fail to reject. The first thing I do is bring that evidence. Because 0.079 is greater than 0.05, we fail to reject the HO and do not have convincing evidence that I am a less than 80% free throw shooter. That is our decision and our conclusion. So far, so good? All right, big ideas from today. When we are going to calculate a p-value, you have to check your conditions. Do you guys remember the 4 C's from last chapter? We're going to do the exact same thing here. At the beginning, we're going to choose the procedure that we're going to use. We're going to state our alpha level. We're going to state the null and alternative hypotheses, and we're going to define P. We're going to check our 3 conditions: randomness, 10%, large counts. Then we will do our calculations. Our calculations were this bit right here. Those 2 steps were the calculations that we needed to perform. And then we will conclude, which includes an interpretation of what the p-value is. So this is our quick notes: conditions, 10%, random, large counts. The test statistic, which in this case is Z, is equal to the statistic minus the parameter divided by the standard deviation. And the p-value is the area that gets shaded under the normal curve. So far, so good? Cool. We'll do the check your understanding, and we'll move on to our next activity tomorrow after we grade homework 9.1. Reading pages 600 to 611 will be really, really helpful as we gear up for tomorrow. 600 to 611, 9.1 homework.